Okay, today we're going to talk about the last part of gases and, liquids and solids, and that's going to be vapor pressure as well as changes of state, and we're going to include our phase diagrams in here. Okay, so for a vapor, just to back up here, define some things. It's a gas phase for a substance that exists as solid or liquid at 25 degrees Celsius and 1 atm. So when we talk about, this is something that we normally is going to be a solid or a liquid, but we can force into the gas phase. Heat we know equals enthalpy, so we can look at what's called the delta H of vaporization as the energy required to vaporize 1 mole of a liquid at 1 atm. And evaporation is endothermic because you're raising the kinetic energy of those particles by raising the temperature. Water has a very large delta H of vaporization, and it's what we've seen because it's so polar and it has such strong hydrogen bonding. It takes a lot of energy to convert liquid water, to a gas. Okay, now when we talk about vaporization, keep this out of the way here, initially, if you put liquid into a closed container, okay, so here we put some liquid in here and we closed it off. Initially, the liquid volume will decrease as the molecules start to enter the gaseous phase. So as soon as you pour them in, the amount of liquid will decrease as these start to, as some of them will escape into the gas phase. When equilibrium is reached, no more net change occurs. So that means as fast as things are turning into a vapor, other things are condensing back down. And right at the surface, that always happens when you look at it from a molecular level. So essentially, the rate of condensation and vaporizations are equal. Okay, so that's what we're looking for. This is our equilibrium condition here. Now the molecules are still changing phase because equilibrium is dynamic, but like I said, right at the surface you're going to have as many particles escaping into the liquid phase as those that are condensing back down into a gas phase. Now we can look at vaporization. Here is the rate, which is how fast things happen, and here is time. So if we were to plot that rate of evaporation that pretty much just stays the same, you're consistently going to have those molecules that will be evaporating. The rate of condensation is going to increase until those are equal. Okay, so this is what we call equilibrium vapor pressure, just meaning that the pressure exerted by that vapor pushing back down is going to be the same over time. Now with vapor pressure, okay, the vapor pressure is defined as the pressure of the vapor phase at equilibrium. Okay, so pressure, vapor pressure, that's where that comes from. We can use this using a simple barometer. All right, and so, here the barometer, again, by how much the air is pushing down depends on how much everything is kind of rising up into that tube or not. So liquid can be injected under an inverted tube, and part of the liquid will evaporate to the top of the tube, and this can be determined by the height of the mercury. And so this is just showing you some of the differences. Instead of using water vapor as kind of our standard here, we've got mercury. Okay, so for example, this is just showing you water. Here we've got an alcohol, and then we've got one other compound over here. It's just showing you the difference between the vapor pressure as you go for these different substances. All right, now with vapor pressure, if something is what we refer to as a volatile liquid, it's a liquid with a very high vapor pressure. And again, when you think high vapor pressure, you just got to be thinking lots of gas particles that can then push back down. They will evaporate very, very, very quickly because they have very weak intermolecular forces. Okay, this is, for example, when you go to the gas station. Okay, the octane spills out onto the ground. It immediately evaporates. Those forces are so weak that it has a very high vapor pressure, and it's going to be volatile. And this is just a general perspective, but if you have strong intermolecular forces, it's going to have low vapor pressure. It means that not a lot of particles are going to escape into the gas phase. If it has a large molar mass, it's also going to have strong intermolecular forces, or stronger intermolecular forces, since there's more electrons available to be polarized. Regardless of what the size of the atom is, you've got more electrons that are available to interact in those intermolecular forces, so you also are going to have low vapor pressure. And obviously it would be opposite for those that are volatile or that have weak intermolecular forces. Okay, vapor pressure will increase with temperature simply because you have more molecules that can have enough energy to overcome the intermolecular forces. So if you increase the temperature, you're going to increase the pressure. Okay, so that's also just kind of a gas law relationship that also makes sense for vapor pressure. Oh, where am I here? Okay, now with vapor pressure, if you graph vapor pressure versus temperature, it's going to be nonlinear, okay, meaning it's not a straight line, so it's not a definitive straight line type scenario. And this next graph, where you can get the straight lines, and this really isn't all that important other than I'm just going to explain the relationship to you, is that when we look at things from a mathematical perspective in science, a lot of times we rearrange them with mx, y equals mx plus b in order to get things as a straight line. It just makes it easier to look at. Now, this is just the natural log. Don't worry about the math, but you've got your vapor pressure at temperature 1. You've got your delta H of vaporization. This is the ideal gas constant, 1 over the temperature. And then we've got plus RC on the other end. Okay, so don't necessarily worry about memorizing this. I'm just showing you the relationships. Your book goes into more detail on these if you want to look at it. So, okay, solids also have some amount of vapor pressure. Sublimation is when solid goes directly to a gas. Okay, for example, dry ice is carbon dioxide, where it goes directly from there. And now heat of fusion. Now, this is the enthalpy of fusion and the enthalpy change at the melting point. Okay, so I always feel like this should be opposite because I always think of fusion and putting things together, but this is really the energy related to melting something at one specific point in time. Okay, so it's the enthalpy change that occurs at the melting point. And so if we look at these from our heating curve, we've seen these in the past. This is the plot of temperature versus time where energy is added at a constant rate. And when we look at some of these patterns, this is for water. Here you've got solid ice. Here you've got the liquid and the solid. This is our melting point / freezing point. We saw these last year as well. Here you've got liquid only. Here you've got liquid and gas. And this is the boiling point. Well, it's a bad B. And then this is gas only. Okay, so just to show you where those states are. And as energy, if we think about starting over here, as energy is added to the solid, it's used to increase the temperature of that solid until it reaches the melting point. And when reaches the melting point, energy added is all used to change the molecules from a solid to a liquid. So the temperature doesn't change while it's melting. Okay, it actually would stay right at 0 degrees Celsius while it was melting on some of these. Okay, now if we keep going to the right of that heating curve, after all the solid turns to liquid, okay, which is right here, the energy is then used to increase the temperature. So again, we have all liquid during this phase right here. When it reaches the boiling point, energy is then used to change everything from a liquid to a gas. So again, while it's boiling, it actually stays the exact same temperature. After everything is a gas, the energy is then used to increase the temperature again once we enter that gas phase. Just as a quick note, if you compare them, the plateau from solid to liquid is always shorter than the plateau from liquid to gas because it requires much less energy to go from a solid to a liquid than to go from a liquid to a gas, and that just has to do with density. Remember, gas particles are going to be thousands of times less dense than liquid and solid, and that's why there's less of a jump to go from a solid to a liquid than to go from a liquid to a gas. So in general, the delta H of vaporization, which is the energy required to vaporize 1 mole of a substance at its boiling point, versus the delta H of fusion, which is the energy required to melt a substance, is always going to be a larger amount because there's a bigger jump to go between those states. Okay, now for the heat of fusion, this is the enthalpy change again that occurs at the melting point. So you've got for your compound, its melting point, for example, oxygen, its enthalpy of fusion, or delta H fusion, okay, 0.45 kilojoules per mole. Again, as soon as you get up to these higher intermolecular forces, right, if we're just moving down here, oxygen is nonpolar, so it's pretty low. We start to get into some more polar molecules and polar bonds. we get to hydrogen bonding with water, then we get to some of our ionic compounds, which the difference between these is going to be due to the sizes of those atoms that we saw with Coulomb's law. Okay, so it's just showing you how that energy will go up based on, it's essentially a reflection of the intermolecular forces. Okay, melting point is the temperature when the vapor pressures of a solid and liquid are equal. If the vapor pressure of a solid is, here's some options, less than that of the liquid, the temperature must be greater than the melting point, so it must be a liquid. If the vapor pressure of a solid is more than that of a liquid, the temperature is less than the melting point, so it's going to exist at a solid. And if it's equal, then they can or they will coexist at that point. Oops, boiling point is the temperature when vapor pressure equals 1 atm. So that's essentially, this is part of the reason why some things at higher altitudes can boil at lower temperatures, because the 1 atm is usually general sea level atmospheric pressure. So if the vapor pressure is less than 1 atm, no bubbles can form because there is too much pressure on the surface, so it won't boil, in essence. There are some exceptions, as always. You can have things that are what we refer to as being super cooled. This is a situation where substance can stay a liquid below the melting point because it doesn't essentially achieve the level of organization needed to make a solid yet. And this is when you cool something really, really, really fast, and we're actually going to use some of this next semester, but so it super cools. This is where we would expect it to level off, but it goes down faster until it can start to crystallize, and then it will actually come back up. It's really just an exception to temperature changes. And then superheated, when something is again heated too quickly, the liquid can actually be raised above the boiling point, and we manipulate these things for different properties of substances and materials. So. Okay, last but not least is phase diagrams. Phase diagrams represent phases as a function of temperature and pressure. So it's really in a closed container, so this is not a real life situation. On each line, both phases exist, and at the triple point, all three phases exist. For example, in the liquids and solids at that point, we'll have the same vapor pressure. So let's see some of these. Okay, let's look at some. So in general, before I kind of get into it, you always have pressure on the y-axis, you have temperature on the x-axis, and there will be some general similarities to it. This is usually your solid phase, okay, over here. For example, if the combination of the pressure and the temperature is below those values, here is your solid phase. Here is your liquid phase, and here is your gas. Okay, and so this is what's called the critical point. Up here, this is where we get something beyond its limits, so to speak, and we're going to talk about this here in a minute. But those are the basic standpoints, and when I do the together problems, it will help illustrate this as well. Now, most substances have a positive slope at the solid-liquid line because solids are usually more dense than liquids. Okay, that's usually the typical pattern. However, one of those exceptions is water. Okay, water actually has a negative slope, and we've seen this 1,000, maybe more than that, times, but not known it. This is just because solid water, ice, is less dense. So this is why ice floats on the surface of liquid, on liquid and water. There's chemistry that goes into it, but obviously, but it's just talking about the fact that that the solid is less dense, so that's why it's got this negative slope to it. Okay, and this is just showing you, here's our triple point where all three phases exist. Here's our critical point, and just some different things that we can look at. Okay, here is also the boiling point right there where you have 100 degrees Celsius. Here's your melting / freezing point, and you can read these graphs in order to figure out what phase that substances would be in. If they give you a temperature and a pressure, you can follow the graph to determine what phase that substance would be in. Okay, and again, this is just showing you, I'm not sure why this is there. It's right out of your book, though. I think it's just showing you different spots and different places where things exist. And then the critical point, I know I mentioned before, this is if the temperature is increased, the vapor can't be liquefied no matter what pressure it's applied. So this is really just an extreme high temperature and high pressure situation where we can manipulate things. It's at the end of the liquid gas line. Only one essentially fluid phase exists that's really neither a gas or a liquid. It's what we refer to as a supercritical liquid. I'm not going to go into much more detail than that right now because we don't necessarily need to understand it. Just know that it's past the critical point and it's neither a gas nor a solid. Okay, hope that helps, and look out for the